Section 5.5, graphs of tangent, cotangent, cosecant, and secant. So, first we're going to graph tangent. I've picked some values. Please remember that when we're trying to find the tangent of negative pi halves and pi halves, remember that via our definition you get division by 0. And so specifically tangent of negative pi halves is undefined, and therefore the ordered pair is also undefined. Now, we can also go ahead and interject that the deal is that because we really have a division by 0 situation, recall that division by 0 creates vertical asymptotes. And so since that's the case, I claim that we can go ahead and sketch in the vertical asymptote that will occur at negative pi halves. Then, tangent of negative pi thirds, well, that's going to be negative root 3. Now, for this, I have approximated it to negative 1.73, so that when I plot my ordered pair, negative pi thirds, it can help get me a little closer. So that's about right here, okay? Then, we plug in negative pi fourths into tangent. Tangent of negative pi fourths is negative 1, and so then, of course, we get that ordered pair. Negative pi fourths, negative 1. Then, tangent of negative pi 6, well, that's going to be negative 1 divided by root 3, or for the purpose of graphing, approximately negative 0.58, and so that's going to be about right here. Then we plug in 0 into tangent. Tangent of 0 is going to be 0. Thus we get the ordered pair 0, 0. Then, tangent of pi 6, well, lucky for us, that's just going to be 1 over root 3, and so that's going to be pi 6, 1 over root 3, where 1 over root 3 is about right there. Then, tangent of pi fourths. Tangent of pi fourths is 1. Tangent of pi thirds is root 3, which is approximately 1.73, so it's about right here. And then we plug in pi halves into tangent, and once again that's the division by 0 situation, and therefore it's undefined and the ordered pair doesn't really exist, but strictly because of that division by 0, we get a vertical asymptote. Now, recall that with vertical asymptotes, the situation is that you must approach the vertical asymptote. And so what happens is that as I connect these dots, this function will look something like this. And it's going to approach that vertical asymptote, but it's never going to cross it. Okay? And so this is what one period of our tangent function will look like, specifically the period between negative pi halves and pi halves. Now, copy and paste that forever in both directions. What do you end up getting? Well, you get something about like this. And so this is where it goes forever. Now, real quick, just to throw in the fact, remember that there's going to be a vertical asymptote here, 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 and then so on and so forth. So specifically recall that our domain for tangent is going to be all the real numbers except for pi halves plus integer multiples of pi, right? Because remember that our period of tangent is pi, and so those values get kicked out. And specifically now we can state that we have vertical asymptotes at the values x equals pi halves plus integer multiples of pi. Now, you could also state that slightly different. We do also get vertical asymptotes at odd multiples of pi, and that just happens to be that the arithmetic works out that 1 pi halves, 3 pi halves, 5 pi halves, 7 pi halves, and the negative version, so on and so forth, are every location of our vertical asymptotes. Then, it's easier to see that our range is going to be from negative infinity to positive infinity, because of course we do cover all y values here, thanks to the asymptotes. This thing is symmetric to the origin, therefore it's odd, and if you wanted to check this out, you could either turn your screen upside down as long as you didn't have rotation on, or you could turn upside down on your head and you'll see that the image upside down is exactly the same as it was right side up. It's origin symmetric, which means tangent of negative x is equal to negative tangent of x. The period, once again, is pi. Notice that if I take the midline points from here to here, that's a distance of pi. If you would rather, you could measure from asymptote to asymptote. Still, period is pi. Our x-intercepts, they're going to occur at integer multiples of pi. So integers being all the positive and negative counting numbers including 0. So 0 is included here, so is pi, 2 pi, 3 pi, so on and so forth. Notice that for tangent, our y-intercept is the origin, 0, 0. And there's no maximum value because it goes up forever. There's no minimum value because it goes down forever. And since there's no max and no min, tangent does not have an amplitude. So let's give this a shot. Let's say that I want to graph tangent of x plus pi fourths minus 1. And so we're going to do this one pretty quickly. We're not going to worry with our key points. Now, realize that our key points are going to be very similar. Actually, I claim that if you picked the same type of key points that we used previously, you could get pretty close. That would give you one full cycle and then you could repeat. But we're going to do it easier than that. We now know what our parent function looks like. So our parent function is tangent of x. And what does parent function look like? Well, tangent looks like this. And then it just repeats over and over, right? Copy and paste that thing, and it continues again, so on and so forth. Now, since that's the case, let's just notice what transformations we have. Let's not work ourselves to death. What is this? Well, that's a phase shift. Specifically, because it's plus, it's opposite what we would think, and so it actually goes left a distance of pi fourths. Alright, so we know we're going to take the tangent function and we're going to shift it left pi fourths. And we also have this, which is going to make it go down 1. Alright, so that's our transformations. Left pi fourths and down 1. Now, let's give ourselves some references here. Negatives down here, positives up here. And so let's think about this a moment. Well, what happens? Alright, well, just to remember, where did our vertical asymptotes occur before transformation? Well, they occurred at negative pi halves and at pi halves, and then every addition of pi integer multiples to pi halves and negative pi halves. Alright, but then, if this is pi fourths, and we shift left pi fourths, where did our vertical asymptote move to? Well, if we just shift it left pi fourths, then our vertical asymptote will, instead of being at pi halves, will be specifically at pi fourths. And then the vertical asymptote that was at negative pi halves is now at negative 3 pi fourths. Now at this point, just take the distance of pi in every direction from our vertical asymptote and you'll get the matching ones. Now notice that because of this setup, each tick mark here ends up being pi fourths, and so 4 tick marks to the right or left ends up being where vertical asymptotes are. So 1, 2, 3, 4. So I get a vertical asymptote here. And then 1, 2, 3, 4. I get a vertical asymptote here. Alright, so now we've got our phase shift almost fixed. Alright, but then let's think about what happened. Well, we also have to deal with the fact that things shifted down 1. And so notice that this fixed point here would be shifted down 1 in addition to the fact that it was shifted left pi fourths. So I know that I have a point right there. And then of course my center marks are going to be there, halfway between each one of these asymptotes. Alright, then what happens? Well then, we would have had, if this is 1 and this is pi fourths, we would have had that point 1 there, and if this is negative pi fourths, we would have had this point here at negative 1. But those got shifted left pi fourths and down 1, so now they're going to be here and here. So here and here, here and here. And once again. Now at this point I claim we really have enough to get the graph pretty close. And I claim that this is what our tangent function is going to look like. There we are. Now, let me give you the computer-generated image so that you can see that it's exactly what I say it is. Look at here, I claim the blue here is exactly the same as the blue that I just had. Notice that what happened is exactly what I said. This point that was originally that point on the red one shifted left pi-fourths and down 1. And so that was good enough to get a pretty close sketch, and that's what we're going for. Good news is that with my labs, a lot of these are going to be multiple choice, and so we'll look at some of those at the end of this lecture. Now let's graph our cotangent function. And so we're going to graph one section between 0 and pi. Real quick to give us some reference. Alright, so then cotangent of 0 is what? Well, remember that via our definition, cotangent of 0 is going to create an undefined situation because we get division by 0. And once again, exactly the same as tangent, division by 0 forces vertical asymptotes. So, at 0, cotangent has a vertical asymptote. Then, cotangent of pi 6, well, that's going to give me root 3. And so then, at pi 6, I'm about right here. Then, at cotangent of pi fourths is going to give me 1, so I get this ordered pair. Then, cotangent of pi thirds, that's going to be 1 over root 3, and so it's going to be about right here. Then, cotangent of pi halves, that's going to give me 0. Then, cotangent of 2 pi thirds, that's going to be negative 1 over root 3, or about right here. Then, cotangent of 3 pi fourths is negative 1. Then, cotangent of 5 pi 6, well, that's going to be negative root 3, which is going to be about right here. And then cotangent of pi, once again, is undefined due to the fact that the definition gives us division by 0, and so I get another vertical asymptote. Now notice that, of course, our period being pi, things are going to end up appearing, we're going to have vertical asymptotes at every interval of pi, but I claim that our cotangent function looks about like this. And it has that asymptotic property, that is, it approaches those asymptotes and continues forever, but never actually touches or crosses the vertical asymptote. So let's look at computer-generated image. Here we are. Then let's go ahead and sketch in our vertical asymptotes just for the sake of reference. Notice that they're occurring at every integer multiple of pi, which gives us the fact that our domain is going to be all reals except k pi, where k is of course an integer. That's exactly what I said. Integer multiples of pi are out. Well, then we can answer the question, where are vertical asymptotes? But our vertical asymptotes are going to be at the values x is equal to k pi, where k is an integer. And so integer multiples of pi, there we are. Then we see now that our range, or we can verify that our range is from negative infinity to positive infinity. We see that again it's symmetric to the origin, thus odd. That is, if you flipped your screen upside down, you'd see that the image looks exactly the same, except for our numbers being flipped around. Or if you turned upside down on your head, the image is exactly the same as the other way around. Cotangent of negative x is equal to negative cotangent of x. Our period, once again, is pi. Notice that if we measure our distance between vertical asymptotes, we'll get a period of pi. Our x-intercepts specifically are occurring at pi halves plus n pi. Our y-intercepts, well, we don't have any, right? Because the vertical asymptote is at 0, is at x equals 0. And so there's no y-intercepts. And once again, since there's no max and no min, there's no amplitude, So that is our cotangent function. Notice they're similar. Cotangent and tangent are similar, but they're not the same. So watch out for that. Alright, so now let's go through a graph of cosecant. Alright, what can we do? Well, cosecant of negative 2 pi is undefined, right? Cosecant of negative 3 pi halves, that's going to be 1. Cosecant of negative pi is undefined. Cosecant of negative pi halves is negative 1. Cosecant of 0 is undefined. Cosecant of pi halves is 1. Cosecant of pi is undefined. Cosecant of 3 pi halves is negative 1. And cosecant of 2 pi is undefined. Now once again, this is of course because this is the reciprocal of the sine function. Now, I also claim that if you were to sketch the sine function, you can use it to get a sketch of the cosecant function, realizing that you're just taking 1 divided by whatever the sine values are. But let's graph this real quick. Well, remember that anywhere sine is 0, we have a vertical asymptote. Well, sine is 0 at 0, so vertical asymptote. Sine is 0 at pi, vertical asymptote. Sine is 0 at 2 pi, vertical asymptote. Now, if you want some reference, you could sketch in the sine function. Now, I'm going to do it in a yellow color, so it's not very bright, but notice that if I sketch the sine function would be this yellow. I know it's very light, but I don't want it to stand out because I'm really trying to graph the cosecant function. Alright, well, but then notice from those ordered pairs that we just found a moment ago, and this matches up with our sine function, everywhere sine is 1, cosecant is also 1. So we get these cosecant values for free. Alright, well then, what else happens? Well, at that point, you're then taking fractional numbers, 1 divided by a fraction, but 1 divided by a fraction is really going to give you a larger than 1 number. And so really what happens is you end up getting this image where specifically you're approaching the vertical asymptotes. And so it almost looks like there's a bunch of mini parabolas coming in, except that they approach vertical asymptotes. Okay, so they're not parabolas, understand that, but this is what cosecant looks like. And if nothing else, you can, like I said, use sine to get this, because of course 1 divided by the sine value, well, it's going to start growing and growing towards infinity as I get closer and closer to 0. And that's exactly what happens with this cosecant function. So let's see a computer-generated image of this. Here we are. Here's our cosecant function. Once again, for reference, we could of course plot in those vertical asymptotes. Well, once again, this reminds us that our domain is going to be all reals except integer multiples of pi. So those values are out, which of course gives us the location of all the vertical asymptotes being x is equal to integer multiples of pi. And so there we are. There's our cosecant function. Notice now that this verifies what we stated previously about our range, where our range is specifically from negative infinity to negative 1, where of course, notice this is negative 1, and then this is positive 1, and then that's exactly our range. Our range is from negative infinity to negative 1 inclusive, and then union 1 to infinity. Of course, this is symmetric to the origin. That is 180 degree rotation. Makes the exact same image. Turn upside down on your head. Turn your screen upside down. But that means cosecant of negative x is equal to negative cosecant of x. Once again, this property is directly inherited from the sine function. Our period is 2 pi though. So be careful because, yeah, we have vertical asymptotes, but one complete period has to be a full period of 2 pi. Notice from either from one of these to one of these, that's a distance of 2 pi, or you could go from a vertical asymptote to not the next one, but the next one, right? Because you need a complete cycle. And so notice that a complete cycle has a period of 2 pi here. Well, we don't have any x-intercepts. Okay, this cosecant function has no x-intercepts. It also has no y-intercept because of the vertical asymptote on the y-axis. Of course, there's no maxes and mins, and since there's no maxes and mins, there is no amplitude. Then, we can do our secant function. For secant, we're going to get that secant of negative 2 pi, of course, because this is defined as 1 over cosine of x. That is, secant of negative 2 pi is 1. Secant of negative 3 pi halves is undefined. Secant of negative pi is negative 1. Secant of negative pi halves is undefined. Secant of 0 is 1. Secant of pi halves is undefined. Secant of pi is negative 1. Secant of 3 pi halves is undefined. And secant of 2 pi is 1. And so let's sketch that all in. Notice that everywhere we have undefined, because we have that division by 0, we get a vertical asymptote. Now, another way to do this is if you wanted, you could sketch the cosine function in the background. And I'm going to do it again in yellow just so that it kind of hides behind our actual graph. Remember that cosine is at 1 on the y-axis, and then is 0 at pi halves, and then is at negative 1 for pi, and so our cosine function looks about like this, which then tells us a couple of things. Everywhere it's 1, we get secant values, and everywhere it's negative 1, we get negative 1. Then, anywhere cosine is 0, we do get vertical asymptotes. That's our undefined situations. And then we can use the cosine, because 1 divided by cosine is secant. Then we see that what we're really going to get is this image. So blue is our secant function. We approach the vertical asymptotes, and blue is our secant function. Okay? Well, let's do a computer-generated image. There we are. Once again, we can sketch in our vertical asymptotes to help us keep on track. But this is our domain that we previously talked about. That is all reals except pi halves plus k pi. Well, that also means that our domain restrictions for secant are going to be our vertical asymptotes, which means they occur at odd multiples of pi halves. And so notice that that's where we get all our vertical asymptotes. We also now can verify that the range goes from negative infinity to negative 1 inclusive, union including 1 up to infinity. We see that it's symmetric to the y-axis, just like cosine. This is an even function, and remember that's symmetric to the y-axis. Thus, secant of negative x is equal to secant of x, inherited directly from cosine. Our period, again, is 2 pi, right? Somehow or another, you got to measure a complete cycle that you could copy and paste that amount, and you would get the exact same picture. We do not have any x-intercepts for the secant function, just like cosecant. But the secant function does have a y-intercept, specifically at 0, 1. Once again, no max, no min, thus no amplitude. So the only trig functions that have amplitudes are sine and cosine. All the rest, not having maxes, not having mins, don't have amplitudes. Alright, so now let's just graph these just like we would in MyLabs. Alright, so what's going to happen? We're told that we want to find what is the function y equals negative 5 secant of x. First thing that I'm going to do is I'm going to think about secant of x, and I'm just going to sketch for myself secant of x. Now, remember that my sketch here is for secant of x before transformations. Then we have transformations to deal with. So, secant of x looks about like this. Where specifically, we have the vertical asymptotes at odd multiples of pi halves. So, pi halves, negative pi halves, 3 pi halves, negative 3 pi halves, so on and so forth. Okay. But now let's label the transformations that occur. Alright, I only see one transformation here. This one transformation does two things. It's going to make it taller and skinnier. It changes the size, and it also changes the point, because remember that originally we would be on this ordered pair 1, and so that 5 is going to adjust where that point of these parabola-looking objects are. Also, the negative out front is a vertical reflection. And so two things happen. We turn upside down, and we shift our points up to positive 5 and down to negative 5. Okay, so let's get those right. So two things happen. It turns upside down. Alright, so the ones that got turned upside down are here, here, and here. A is out. Alright? But then we get a frame of reference where specifically we need the same vertical asymptotes. We didn't change the period, so our vertical asymptotes end up at the same places. And so notice which one is out. This one's out, right? You can't do that one because this one has a period change. This one changed where the vertical asymptotes were. That's a period change. That's not us. Alright, so now we're down to B or C. But how can I pick which one's which? Well, specifically, remember that this ordered pair here, right here, was the point 0, 1. Alright, but what happened? You take that point and you multiply it by negative 5. So it's got to now be, for this one, this point ends up being the point 0, negative 5. Because you're really changing the coordinate of the y value. You're really changing the y coordinate. And so now I know that it has to be B, because that's the ordered pair 0, negative 5. So B is my answer, and C is out. Okay? Alright, well then, let's consider the domain of this y equals negative 5 secant of x. My claim, though, is that we did not change the situation at all. We didn't do a period change, we didn't do a phase shift, and since we did no period change and no phase shift, our domain must remain the same as our parent function secant of x, which means that odd multiples of pi halves are out. And notice that odd multiples of pi halves are these. Okay, x is everything except k pi over 2, where k is an odd integer. Then we need to determine the graph to figure out the range. Okay, well, notice that our range for our unchanged function would have been from negative infinity to negative 1, and then from 1 to infinity. But at this point, if we glance at our graph here, notice that this is 5, and this is negative 5, and so specifically, what's our domain going to be? Well, in interval notation, that would be from negative infinity up to negative 5, including union positive 5 up to infinity. Well, how can I write that in inequalities? Well, this piece right here is really the y values are less than or equal to negative 5, remember, because bracket is equality, and really union is or, and then this one says y values bigger than or equal to 5. And so that one is, there we are. And so that's our answer. Now let's try one with tangent. So we want to graph the following function, and we want to show at least 2 cycles, and we want to use the graph to determine the domain and range. So we're really doing all the exact same things. Alright, so once again, I like to remind myself of the parent function. And so the tangent function looks like what? Well, the tangent function has vertical asymptotes at odd integer multiples of pi halves. Okay? And so pi halves, negative pi halves, 3 pi halves, so on and so forth. And so I remind myself of where the vertical asymptotes are. And then the parent function of tangent looks like this. Now, and for a point of reference, remember that for tangent, at pi fourths, you got 1, and at negative pi fourths, you got negative 1. Now, this is really to help me keep up with the scale, because if I lose the scale, this isn't going to work out for us. So keep those things in mind. So this is the parent function. All right, so now let's talk about our transformations. So, 2 transformations. All right, so the easy one is up 1. The whole image is going to shift up by 1. And we have a period adjustment. And so remember that our period adjustment, that's going to be our period for tangent is going to be pi divided by 1/4, which really means that our period is going to happen in 4 pi. Okay, alright, so now I know that 1 complete period is going to be our new tangent function. And it's also going to be shifted up by 1. Alright, so let's just go ahead and look through what we've got given here to see which ones we automatically know are no good. Okay, so look at A. Alright, well A looks an awful lot like my actual function, shifted down by 1. And so that's out, because that's a down 1 and no period adjustment. Okay, so that's out. Alright, so then I see that B, C, and D all have shifts up. But notice the scale on D. Notice that the scale here has this at 2, which means that that's a 1. And if that's a 1, this is not shifted up by 1. That was shifted up by a half. And so I know now that D is out. Okay, great. So let's confirm that C's scale works out for us. Okay, so 4 means 1, 2, 3, 4. 1, 2, 3, 4. Great. We now see that B or C is our situation. Maybe. Well, but we just shifted it up, right? We adjusted our period, and we adjusted our location up 1. But we didn't shift it left or right. And so C is actually a phase shift. Notice that that's a shifted left or right because we remember that this point here for tangent, there is that y-intercept at the origin. And so we need to have that point shifted up by 1. It can't be shifted left and right, and so C is out. Let's confirm everything we just said is right. Well, 1, 2, 3, 4. Okay, great. That point got shifted up by 1. That's good. Then we really just need to double check and make sure that this period is right. But to count it, well, if this is 8 pi, then that's 2, 4, 6, 8. So this is 2 pi. This is negative 2 pi. And to check our distance, 2 pi minus 2 pi, well, that's going to give me positive 4 pi, and so B must be my correct answer. Whew, there we go. Then I need to figure out what's the domain of my function. Okay, well, because this graph is correct, I claim that now I just have to figure out where those asymptotes occurred. Well, notice that this was 2 pi, and at negative 2 pi. Okay, that's my new issues. Also, where else does it change? At every 4 pi interval past that. So, at 2 pi, at 6 pi, negative 6 pi. It would also occur at 10 pi. We would also get a vertical asymptote, and at negative 10 pi, we'd get a vertical asymptote. Alright, so let's see which one of these labels that the best. Okay, well, k fourths, where k is a non-integer, that's definitely out. It's not that one. Alright. Then B is k pi, where k is an integer. But notice that if you multiply 1 times k, 1 for k, 1 times pi is pi, and at pi we don't have a vertical asymptote. We also could use 0, since 0 is an integer. 0 times pi would be 0, but there's also not a vertical asymptote there, so b is also out. We also know that it's not all real numbers because we have domain restrictions, and these vertical asymptotes here show us that. Now, this says 2k pi, where k is an odd integer. Let's check that. Alright, well, odd integers are things like 1, 3, 5, so on and so forth. So 1 times 2k pi, or 1 times 2 pi, is 2 pi. Okay, that checks out. 3 times 2 pi is 6 pi. Whoop, that checks out. 5 times 2 is 10. 10 pi, that checks out. Perfect. That is our domain restrictions for this tangent function. Well then, what's our range for the tangent function? Well, the truth is there's nothing that you're going to do to change that the range for tangent function is all real numbers unless you put restrictions on it overall, and so I say that C, all real numbers, is our range.